Uh, we are happy to present my Master Philip in this webinar with the topics posing scientific research, method, and statistics. One of postgraduate University Semarang mission is to conduct research in the context of food science, technology, and art in the field and education and non-education with conservation perspectives and with international reputation. I think the webinar topics today is a crucial part of research activity, mainly about research about collecting data, data analysis, and other. I hope this webinar will continue with other topic in the future. And I believe that this webinar would be useful for all participants in the research activity. Finally, I would like to say happy joining with webinar. Thank you very much, Mr. Philip. Thank you.
Thank you very much, Professor Sugianto from Welcome Speak to Dr. Philip X. Fox. And now, the time for Dr. Philip to present about how to do research. And he is the expert in statistics also because he do the doctor special in statistics, also doctor in sports science. Welcome, Dr. Philip X. Fox. Now the time is yours.
Okay, thank you very much. Thank you to both of you for the introduction and for having me. It's my pleasure. Let's check. So, can you see my screen?
Not yet.
Not yet. Okay. Did I need to turn it on or you did?
You can do by yourself.
Ah, I think I see it. No?
Yes, that's good.
Okay.
How come?
How can? I started learning a little bit Chinese, but not very good yet. Okay, yeah. Good. So thank you everyone for being here. I appreciate the warm welcoming words, and I also hope it will be helpful, hopefully to most of you or many of you. What I will be doing today is a general approach towards scientific research and methods, and then specifically statistics. I think it may be helpful for younger students as well as higher degree students like doctoral students. And I hope at least some messages to take home are there for everyone. The general roadmap for today is that I want to start talking about methods in general, doing a step-by-step go-through, how to design any scientific research and how to implement it. And the general structure of how to implement your research is more or less the same as how to write your thesis. So especially when you're doing a doctoral study and you write your dissertation, or also for master thesis, you need to follow a certain structure. And this is basically the same as you implement the study. So in the first part, I will address these topics. In the second one, it's about validity. And I will talk about some examples of validation studies. The reason is, first of all, because I was working a lot on validation studies recently. The second one is that it's relevant for basically everyone, because most of the time you use some tools of any kind, and you must know what kind of tools you use, and you must check if they are valid for your specific purpose of your study. So it's never bad to know how validation studies in general work. And if you use tools that are new, or you must adapt some tools, then it's quite good, even if you don't commit to a full validation study itself, but it's still quite good to have a first part before your data collection where you confirm the validity of the adapted tool that you use. So that makes your study stronger than just saying it is a good tool and then you make some changes and you hope it's still valid. And the third part is that I want to address some statistical topics, some selected tests. So of course, not all the most common tests which exist, but some specific tests. I want to highlight some difficulties and give some tips on how to visualize the outcomes. So let's start with the methods in general. So first of all, I must clarify that this structure I provide here, following participants, study design, devices, calculations, and statistics, they are not set in stone. So for every journal, this may be different. And for every supervisor, this may be different. And for any application you must send for a research project to apply for fund money, it may be different. But in many fields, and in fields, it may also differ. But in many fields, especially when you collect some data in experiments, and you must present how you collect the data, how you handle the data, this is a somewhat common structure. And the important thing is that you clarify with your supervisor or with the journal where you want to send your work, what is the structure, what is the guidelines they ask for. Going through this structure, it's a common thing to start with describing your participants. The first step is usually after you wrote your introduction section, which ends with your research questions. So during the whole procedure of doing literature research and thinking about what exists already, what are the problems, the deficits, what is missing, you end up with some research questions. And usually you already have some hypothesis, expected outcomes. And then you go into the methodology and you start with what kind of participants do I need to answer these questions, to collect data from. And it's important to have the characteristics of the participants, the number, how they were selected, and then also ethics, how to treat them. In the second step, you must describe the overall study design. What kind of experiments were used? What kind of protocols? Is a longitudinal style of study design? Or how is the general approach of data collection? Basically, this is everything that describes what was done and how it was done. The third point is more specific, what kind of devices were used and what kind of instruments. So very specifically, I used particular force plates from a certain brand, for example, or a questionnaire that was developed in another study. So it's very specific compared to the overall study design. And then in the fourth point, you have finished the actual data collection and you start describing how you handle the data. How did you calculate variables? What variables did you use? How did you process them, like filtering and so on? So everything you did with the data when data collection is finished. And statistics is the last part of it, where you run statistical tests with these processed data, and there you need to provide the software you used, the tests, all the specifications of the tests, and how you interpret them. There are, for many tests, there are definitions of benchmarks, thresholds, what kind of effect is large, moderate, or small. For all these sub-chapters, the important thing is that you need to provide all information that someone else who is reading it can replicate the study. So if you do your study, you describe all these chapters, participants, study design, devices, and so on, and I have no idea about it. I just read it, and based on the information you provided to me as a reader, I can copy your study and I can do it myself. If at any point I try to copy it and then I miss some information and I don't know what to do because I don't know, you didn't describe it, how you did it, that's problematic. Then this is information missing. So the golden rule is provide every information that is required to copy your study. In detail about all these chapters, the first thing for participants is that the characteristics of your sample group must be meaningful to answer the research questions. So you must know what characteristics are relevant for your research question, and you must be aware of any other relevant characteristics, and you must collect them so that later on you can control for them. What I mean by it is giving a very simple, obvious example. If your research question is, you do some gait analysis, for example, how people are walking, and you wonder if older people are walking differently than younger people. And so age is obviously a very relevant characteristic. Basically it's the independent variable for your later analysis. So you must ask them about their age, and you collect the age. In one way or another, you have defined gait characteristics, maybe the speed, maybe some joint angles, whatever is your research topic. This will be your dependent variable. But there may be many other characteristics that are also relevant. For example, if some people have injuries in their lower limbs, this may affect the gait. So certain limb injuries, for example, may be other relevant characteristics. Let's say you are not aware of them, you don't collect this data, you just check your gait parameter, maybe speed, and you just ask for an age, and then you run a simple test. For example, a correlation between the gait parameter and the age. The fact that in your sample, some people may be injured and some people not, may mess up with your statistical outcome. In this case, it is good to know about this, to check in advance who is injured, what kind of injury, and one way is to remove all the people who are injured. The other way is to add the injury as a factor in your statistical analysis. Later, maybe more about this. But the basic important thing for now is that you must know what characteristics are important and potentially influential for your analysis. And you must collect them. If you don't collect them, you cannot fix anything later on. If you have them, you can either change your sample or fix it later in the statistics. The second important point is the sample size, the number of participants. The one thing what you can do is to see what other studies did, how many participants they invited for similar studies, similar statistical tests. The other thing, and in general, in my opinion, the best way is that it is somewhat an unwritten rule, especially in sports science. Hopkins was writing about this a lot, to have a sample size that achieves a statistical power of 80%, finding medium-size effects with a likelihood of a p-value of 0.05 or lower. So you can do statistical power analysis. One example of such free software is G-Power. And you can choose your statistical tests you will run, and you can enter. So when you decide a test, you can enter the parameters you want to achieve. For example, the statistical power, 1 minus beta, being 0.8, reaching medium effects for your statistical tests, and defining the p-value at 0.05. And then the software will tell you what is the required sample size to achieve these statistical values. And this depends on the statistical tests. I don't know them all by heart, but I think for correlation studies, for example, or correlation tests, normal Pearson correlation, I think it was something like 23 or 24 or something like this, achieving these statistical values. So this is independent of the topic you do research. This is dependent on the test and the statistical values you want to achieve. Basically, this is the best approach in my opinion, because when you get criticized or reviewers or your supervisor or whoever questions the sample size, and they ask, oh, is this good enough or not, and so on. This is a very strong argument to say, yes, this was the right choice to use the sample size, because the power analysis said this is the sample size we needed for our statistical tests. Of course, there are other non-statistical reasons to get a larger sample size, or not really a smaller one, usually a larger one. But that's a strong argument. So I would always recommend to do power analysis and to add it into your thesis or your article. The third point is the selection process and the selection criteria of your sample size, how the participants were selected. And the important thing is to be clear if the selection processes affected your sample, basically. Let's say if you collect any kind of data through an online questionnaire, then the sample may be biased towards people who are more familiar with online technology. Probably you will get less, let's say, very old people, or generally people who are not so much familiar with online stuff and technologies, than if you go outside in the street and you randomly ask people. So the selection process may affect your sample. And this is just important to be aware of it. And this is why it's important to clarify how the sample was recruited. If you are in a sports department, and you ask students, it is very likely you will end up with a high number of sports students in your sample, and so on. So this is problematic when it comes to making conclusions for a general population, but in fact your sample was not representative for a general population. And the last and a very short and simple point is the ethical point. Basically, just inform yourself before doing something what you need to do, what guidelines you need to follow to implement your study. Because journals have ethical guidelines, institutions have ethical guidelines. So when you want to implement your study, ask the supervisor, ask the ethics committee at your institution what you need to do so that everything is fine, especially when you work with human beings, obviously. The next point about study design, experiments, protocol, and intervention is the question you should ask yourself is, does your approach, your study design, allow to find the answers you're looking for? So what you do during data collection or during intervention must help you to answer the research questions you asked in the introduction. Let's say if you make a plan how to collect data. You go into a lab and you have an idea what to do. And afterwards, depending on the outcome, you still cannot answer the research question, then you're doing something wrong. You must be certain you are addressing the right things, and you must be able to answer the question afterwards. It can be a positive answer, a negative, this is not important, but you must be able to give an answer. The second point is check if you follow the best practices and common guidelines or recommendations in your experiments. Usually for almost everything, there are some best practices and there are some written guidelines and recommendations by institutions, by associations, in previous studies, how to do certain stuff, how to do EMG analysis, how to put the markers on the body. Basically almost everything, for everything you find recommendations how to do it properly. And it's a shame if you do your study and afterwards you find out, oh, this one step I didn't do in the best way, but everyone, because it's published, everyone knows how it would be in a better way. And then you kind of need to do it again. That would be quite unnecessary. The next part is about validation. Are the things you use, for example, the protocols or the training regimes and so on, are they validated by previous research? Especially, this is important for any tools you use. If you use devices for collecting data, for example. And one thing I want to address, which is sometimes forgotten, is that it's not enough to pick a study where a device was validated, and in the conclusion text, they say it's a valid tool, and then to think that it's valid for every purpose. Maybe your purpose, your measurements are different, or the variables you calculate are different. And sometimes, although a device was validated in a study, it may be not valid for your purpose or for your variable. For example, if you use a tracking tool where you have cameras in a gym and you have chips in, for example, in the shirt of the players, and you track the positions of the players. There can be a study published saying it's this tracking tool is valid, it works, but you must check what have they done. And maybe you find out, oh, they checked the tracking the positions. This is basically what the system is supposed to do. And they run all the validation analysis based on the positions only. So maybe they compare the position from this system with another valid system. But maybe you want to calculate the speed of the players based on the position. And so you use the same system. The system tracks the position and you calculate the speed based on the position. But the other study never investigated and never said that this system is valid for measuring and deriving speed. So maybe it doesn't work at all for speed. Maybe the measurement frequency is too low. It works fine for position, but not for speed. And in fact, this is not only a fictional example, this is reality in especially for tracking position. Acceleration data is usually horrible for position tracking by local position measurements. So they may be valid for positions, for speed sometimes, but acceleration usually is horrible. So very carefully check if it is valid for your purpose and the variables you calculate. Then another question you should basically always ask yourself whenever you do something is if the decisions you made, if they are based on rationals and supported by references or good reasoning. Whenever you make a decision to do something this way or another way, ask what is the reason why you do it this way and not the other way? Because otherwise other people will ask these questions. Your supervisor, people who examine you, reviewers, they will ask, why did you do this? Why didn't you do another way? And only if you have a good answer, you can be more confident that what you do was meaningful. Otherwise, it's better to check in the literature if there is a rationale to do it in any potential way. As long as you haven't done it yet, you can still change the plan. So always ask, why do you do it this way, not the other way? And then the last question is, and basically this goes for the whole method section, is everything you do described with sufficient detail to replicate the same procedure? As I said again, you must be able to provide all the information so other people can copy your study. Okay, about devices and instruments. This includes any type of equipment, tools, models, or also algorithms. So it doesn't need to be something you can hold in your hand or something materialistic. It can be algorithms, any kind of information, a questionnaire, any online tools, and so on. So you must provide information about everything you use. Then, as I said, clarify if they are valid for your specific purpose and your use case and your variables you use. Does the sampling frequency allow for meaningful data for your particular purpose? As I said, in LPS, local position system, when you track the positions, there very often the sampling frequency is basically too low to calculate acceleration. So it's good enough for positions, it's mostly good enough for speed, but when it comes to acceleration, it's getting quite bad. So especially when you do high dynamic stuff, the sampling frequency is very important. And last, do you use the tools properly? Do you use them in the right way? And you can easily find online in other studies, instructions, guidelines, recommendations, how to use things properly. And a very good example where this is very relevant is EMG data, because it's known to be more difficult than other things to collect EMG data in a clean and correct way to get clean, solid data, and to limit the noise. So these are the questions you should ask yourself about devices. Last two topics, calculations and statistics, I don't go into too deep because I will do later on. So the first point is, when you have your set of data, usually you cut the data. You have sometimes starting points, points in between maybe, and an end point. So for example, if you investigate a punching movement, like a boxer, you collect the punch in the laboratory, and then it's not enough to just randomly start anywhere where you and your eye thinks, oh, now it's starting. You must define the start point. The same goes for the end point. Maybe the end point is when the target is reached, maybe when there is no force measured anymore between the target and the fist. So this could be a meaningful end of the strike, and so on. But the cutting points must be clear and defined. And this is usually one of the first steps, and at least before you do filtering. Otherwise, you have errors in the beginning and the end of your sequence when you do first the filtering and then you cut them. So the next point after cutting is filtering. You don't need to filter always all data. It depends on the data. And again, check instructions, guidelines, and so on for your specific data, whether filtering is necessary and what kind of filtering is usually recommended. So there are different types of filter, bandwidth filter, low pass filter, high pass filters, and so on. And usually there are recommendations which one to use for example, ground reaction forces, for kinematic data. It differs. And then you must specify a filter frequency. And here again, what you can do is check other studies, see what they have done, and say you use the same frequency, and then you use the study as a reference. What I think is a little bit better is to find the optimal frequency for your individual data. And you can use this by using fast Fourier transform or residual analysis. These are two techniques where you can find the optimal filter frequency for your specific data. The reason why I think this is a little bit better than just using a frequency that was recommended in another study is because the data in all studies differ and the optimal frequency may be different. So what you do with both of these techniques is finding the best frequency for your individual data. Data. And this is obviously also a stronger argument if you are asked by a reviewer or supervisor why you use this frequency. It's because this was found by the residual analysis, or the FFT, was found to be the best for your data. It's a stronger argument than if you say, well, because others used it, and then maybe the reviewer or the supervisor says, oh yeah, but this other study is not good, and others used a different one, and then you have a problem, right? Then you get into making arguments and so on. And maybe you did some error. Maybe this was a horrible study, and usually you should use a different frequency. That would be quite bad. Then the next part is the question if you need to smoothen your data. And I want to, I will go into a little bit more details on the following slides, because smoothening is not the same as filtering, and it's important to understand the difference. But for now, you should just realize that smoothening is usually only for visualization if you want to present your data. but not for processing your data before doing statistical analysis. I will explain it later. What are the differences and why it differently affects the data? Then the next logical step is how you handle outliers. I will also give more details about how to do it. Use clear definitions. In the best case, you use the definitions that are already in place, that are common, and use valid calculations. If there is something in place already, there is no need to come up with something new. And the derived variables that are meaningful for your research project, research topic should be used and clarified in this section. So we will talk later about the filtering and smoothing and how to handle outliers. And let's start here with abnormalities and outliers. So it depends on the type of data where you find something abnormal in the data. So we are now at the stage that you collect the data and you find in your data, it's not very smooth. There seems to be some error, but you're not sure if it is error. And the question is how to handle it. So let's take the example of collecting ground reaction forces when measuring a jump movement. This is very, very common. And you have instantaneous data, a graph, which looks in the best case kind of smooth. And now in this smooth curve, you have some spikes, which is clearly not a true value. The question is, should you remove them? And you should not remove them prematurely. The first thing you should check is your filter method, because usually the filter is supposed to get rid of exactly these spikes. So if you have these spikes after filtering, check if you used the right filter, if you use the right frequency. Maybe for the frequency was not high enough or low enough, depending on high pass or low pass filter. So maybe it requires adaptation in the frequency. The second part is to check the processing of how the data was collected and then also handled. Maybe it was just a human error when you have single data points. Maybe the first plates were touching each other, or any potential errors. Check for the errors. And only if you can exclude human error and you did filter properly, then if it is possible, you can by hand remove the single spikes. That is how I would approach it. It's a completely different story if you have abnormal observations or deviations in characteristics of your sample. Let's say commonly these would be independent variables, for example, age, or gender, or something like this. And the question is then what you need for your statistical test. In many tests, for example, if you compare two groups with a t-test, in many of these tests, you require homogeneous data within the two groups. So if you want to have females and males, and you want to see a difference, you want to have them within each group very similar, but the groups itself very different. Obviously, in gender, you can have no real deviation. I mean, someone is female or not, or someone is male or not. But it's a completely different story when we talk about young and old, for example. So if you want to compare young people with old people, it would be good if both these groups are very different in age. So they are very young and they are very old. And within both groups, the age has not a large variability. So the perfect scenario would be they have all the same age, and the same in the other group, all the same age. So maybe they are all 80 and they are all 20. So if in the young age group you have, let's say, 20 people, and 19 are 20 years old, and one is 30 years, then the 30 years guy would be an outlier. And then the question is if this affects your analysis. And usually you want to remove outliers. And so there are some discussions whether removing outliers is a good thing or a bad thing. Removing outliers for the purpose of making your statistics look better is obviously a bad thing. Removing outliers because they are not representing what your study is supposed to investigate, that's for me an absolutely fine thing. So if you want to investigate, for example, the comparison between young and old, and in the young group you have someone who is not really young, or maybe he's even 40 or something, so this is what we perceive as an outlier, then I think it's a good thing to remove this outlier from the analysis, because this is basically not what you meant to investigate. When we assess fluctuations, variability in a system for the purpose of finding out the accuracy and the precision of the system, then it's a completely different story. Then we don't remove it. Because when we want to assess a system for accuracy and precision, then we want to know how much and how often do you see these outliers. Then this is a problem of the system which you want to investigate. And this is the part that happens in validation studies, of course. This is the purpose of validation studies, to see how accurate and how precise are systems. And this is why I also want to talk a little bit about this. Outliers can mess up with your statistics. That's the reason why you want to remove them. And when you have your data set, there are different ways how to identify outliers. You can, as you see in the upper part, you can highlight them with color, or you can visualize them, display a figure. I prefer the visualized way, but for any way you use, the general rule is that an outlier is defined as any value, any data point that is larger than the mean of all data plus 2 times the standard deviation, or smaller than the mean minus 2 times the standard deviation. This is what is mostly widely accepted as the definition of an outlier. And you can apply this, this rule to highlight the data, or visualize it, see it, and then in the figure see, oh, okay, this is higher than the mean plus 2 times standard deviation, or lower than mean minus 2 times standard deviation. So when you see these outliers, you must ask yourself, what is the reason, the source of this error? Because maybe there were some other errors that you must avoid. Usually you should remove all errors in the data that represent not the true value in this movement, so which is a measurement error. You do not want to remove human errors. That's your problem during the data collection. Then you should avoid these, but you want to remove all the errors that were due to measurement. And filtering is what is doing this. It removes the error. As as the word filter says, it filters the error out of your data. When doing filtering, you define usually a frequency, and everything below or above or in between two frequencies will be removed. So your data signal is split into frequencies, and based on other research, we know in what kind of data and what kind of movements, what type of frequency are measurement errors. And these are the frequencies we want to remove. So the important thing to understand is that filtering removes specific frequencies from your data that is associated with measurement error. It does not affect the other frequencies in your data. It leaves them. It doesn't even touch them. This is very important. After the filtering, what happens to your data is that the curve you see, for example, the vertical ground reaction force, this curve looks smooth afterwards. If you use a low-pass filter, for example, only frequencies below the threshold frequency will pass, will remain. All the frequencies above will be removed because they are error. And afterwards, your curve looks smooth. The lower your frequency in a low pass, or the higher the frequency in a high pass, the more smooth the curve will look. It's completely different for smoothening. In smoothening, you do not remove a specific frequency of error. What you do is you average across correct, true data and error. And one typical way of smoothening is using a moving average. What you do over in a moving average is that you average over a certain time window, maybe 2 data points, maybe 3 data points, 4, 5, 10, whatever. For the sake of simplicity, let's imagine the example of using a 2-window moving average. And you have 3 data points, and the one in the middle is an error. So you have 1, which is correct. You have a third one, which is correct. And the second one is an error and somewhere up there. The moving average would use the average of the first one and the second one and replace these 2 values by the average, somewhere here. And it would do the same for the second one and the third one. So the average would be also here. So obviously, you do not remove the error, but you will use the error and average errors and true values. Afterwards, the curve looks also smooth, but the whole curve is slightly biased by the error values. So filtering and smoothing is completely different. And what you should do is to filter the data to the best knowledge and a degree possible. And smoothening in general, you should only use when it comes to how to display your data for an audience, for a presentation, for example, for a funder who gave you the money and you need to present the data and so on. Smoothening is just for how the data looks. It doesn't remove the error. This link I sent, which is in the middle, Sinclair, Taylor, and Hobbs, they display and describe both ways of optimizing your filter frequency with the FFT or residual analysis I mentioned earlier. So this study alone is enough, I think, for a doctoral student to understand how FFT analysis and residual analysis is done and to do it by yourself, to find your individual optimal filter frequency. The last point, statistics, verify all the software you use. Make sure that you use the right statistical test for your methodology, your sample, and the type of data you have collected. And provide all information about the tests that are necessary to do the same tests. For some tests, it's simple. They basically don't have a lot of specifications. For others, it's different. For ICC, for example, there are different types of specifications. And if you only write, I did an ICC, no one can replicate it. And then define the interpretation benchmarks. Define what value is considered a high effect, a moderate effect, a low effect. These are the things to clarify in the statistics. Regarding choosing the right test, I know that for many students, it's difficult to know which test to use. There are online many different types of test trees, because like they look like a tree with different branches and so on. And you can search in Google for statistics test tree, and because each is different and maybe you like the one or the other. I like this one quite a lot, and I want to explain to you how it works. And I think it's good to save this, to keep this in mind, or to find your own test tree online, which you prefer. It helps you to find the right test for your data. So this test leads you through a number of questions, and it ends with one particular test to use for this type of data. The first question is, how many outcome variables do you have? And basically, the first question on the left side is, you have one, or you have two or more. I try to use. Oh, do you see my mouse?
Yes.
Yes, we do.
Okay, good. So this is the first question. How many outcomes variables do you have? One or two or more? And if you, let's say, want to investigate how alcohol is affecting your sprint time, then you have one outcome variable, sprint time. So you're here. And then the next question, number 2 here, is the type of outcome. Is the outcome variable continuous, or is it categorical? Categorical would be fast, mediocre, slow. But you collected the speed in kilometers per hour or meters per second, so it's continuous. And then the third question is, how many predictor variables do you have? Oh, maybe is the answers are 1 or 2 or more. And then you may have collected 2 different groups. Oh, so you have 2 or more. And so on. So you can go through this step by step. And in the end, on the very right side, you find all the most common tests, let's say. Of course, statistics is a huge topic, and there are more statistical analysis than these trees include. But these are all the most common basic tests, I would say. So you have the Mann-Whitney-U test, Pearson correlation, regressions, ANOVA, ANCOVA, and so on. This is a little bit closer to see a little bit better for you. The last questions, and then on the last question is specifically for your data, if the assumption for the test is required. So you must know what are the assumptions, but very often it is the data normal distributed? Do you have homogeneous data, and so on? And then, yeah, it's very simple. It tells you, okay, if you follow all the trails through this statistical test tree, in the end, you will know what type of test you have to use. So I think it's a good thing. No need to learn everything by heart, but to know and to understand the differences, and then you can use it. I was previously talking about systems, accuracy, and precision, and I want to go a little bit into detail there because it's a good for scientific practice, a good example for how to use outliers and how to handle data. And you will also need it in one or another way, even if you don't do validation studies, because you basically almost always use some sort of tools and they are validated or not, and so on. These 4 pictures that you see with the target, with the aims, are the usual pictures that you find often online, and one of them is incorrect. The first one is displaying accuracy and precision. All the shots in the center. The next one shows the shots were not accurate but precise, and there you can see what is the difference between precision and accuracy. Precise is if you hit something every time the same time, very similarly. So a system is very precise if it reaches the same outcome every time after repetition. But it doesn't mean that it's accurate, because maybe you miss the goal, miss your target every time. Then it's not accurate, but it's still very precise. On the very right side, you see if something is not precise and not accurate. So it does not hit your target, which means not accurate, and every single hit has a variability, which means it's not precise. The third one, which I placed the cross above, is some people think that if something is more or less hitting a target, but with a huge variability, then it's not precise but accurate. In fact, this is not correct, and there is also some good commentaries and studies published on why this is not correct. To make it short, something cannot be accurate if it is not precise. You need precision to be accurate. If you have a huge variability and you randomly hit anything, so this is very imprecise, then it cannot be accurate. These are the terms you're dealing with when dealing with validation study. Precision is the expression of reliability. If something is very reliable, you will hit precisely every time you repeat it the same spot. If something is valid, it is accurate. When you want to assess validity, you must know how accurately it hits what it claims to hit or is supposed to hit. And what kind of outcome you observe, whether it's accurate or precise or not, you must clarify what is an error by human and what is the error by the system itself, because you want to know how accurate is the system, not the people that use the system. So you must exclude all human errors when you want to know the system accuracy and precision. I want to go a little bit into detail in an example I did recently about position tracking. And then you find these outliers in the data and you wonder, what is the source of these outliers? Was it a human error or a measurement error? And this marker number 23, for example, was clearly an outlier. When we watched the gym, the position of this marker was the one in the red circle. The true values of this one was 20 and 17.5. So this was the position of this marker, and we measured it. But the LPS, the system, told us the position was 19.9 and 19.9 for X and Y. So on the X-axis, we had an error of 10 centimeters, which is somewhat okay. And on the Y-axis, we had this large error of 2.4 meters, which is obviously not okay. If a system tells you a position is 2.4 meters off its true value, then that's not very good. So the first thing I wondered was maybe we placed the marker to the wrong position on the ground. Maybe we confused it with a different marker position, but then there would be another marker close to the 20 meters line on the Y-axis, and we didn't have this. So this kind of error could be excluded. I just tell you this as an example of how to approach data when you observe outliers. You must identify, is it a human error or is it a measurement error? You must identify the source of the error. So as I said, the first possibility that we placed it incorrectly was kind of excluded because there was no other marker at this or near this position. But there are more potential human errors. Maybe the student who handled the data took the data point from the wrong column, or so in the Excel sheet, making some errors, copy-paste errors, or maybe cutting incorrectly. What we eventually found out was that the system integrated a stand filter, which stopped measuring the position when the sensor is moving too slowly. So when we placed the sensor to the position, it stopped measuring already 2.40 meters in advance before we because we moved it too slowly. So there are endless potential sources of error. And this is why I don't want to be too specific about single cases and so on, but you need to identify for yourself what is the source of error when you observe outliers. So when we excluded or removed all outliers and we filtered correctly, then our data looks good. Only then we can start with statistical analysis. And there are many ways of doing statistical analysis. I stick to the topic of assessing accuracy and precision. And what you can do to provide how accurate or precise a system is. One way is to provide descriptive data. For example, the mean, the standard deviation of the one system compared with the other system, or the 95% confidence intervals of the data measured by the one system compared with the other system. You can run intra-class correlation coefficients or calculate them. It's called ICC. The standard error of measurement, coefficient of variation, root mean square error. I go through these one by one. Maybe some of them are familiar to you, maybe some are not, but these are very common ones in this kind of studies. And whenever you are doing a validation study or reading one and you want to understand what they did, Hopkins was also doing a lot about it on on his website, you can find many articles about how to do these statistics. And you can even find a spreadsheet where you just copy paste your data, and then the spreadsheet will calculate some outcome variables that Hopkins finds the most valuable, let's say. But I think all of them have different purposes. And for me, for this session, it's important that you understand that everything has a different reason and purpose, and you must understand the purpose of it to use it correctly. So I don't want that people take a message and they copy paste and that just do the same in their study. That's sometimes that works, sometimes not. It's more important to understand how things work and then to apply it for your own case properly. So I want to go through these and tell you some main features of these. The first one, the ICC, the intraclass correlation coefficient, it is a type of correlation analysis, but it has some strength compared to, for example, Pearson correlation or Spearman. First of all, there are different types of ICC, and for this, it is very important to provide all the informations about the specifications in this test you used. It is, I think, rather easy to select the right type, to conduct it in SPSS. It's very simple, and to report it properly. It's really not a difficult test, but it is a quite helpful one. It can investigate the correlation between more than two items. So if you have a Pearson or a Spearman, you can always only compare the two items. For example, the correlation between age and running speed. But if you have more than two, Pearson on Spearman doesn't work anymore. And the other huge upside of ICC compared to Pearson is that ICC is able to assess the absolute agreement between two or more variables, instead of only assessing linearity or consistency between two. And I will go into detail what is this difference and why it is so important. If you ever plan to use ICC, I can recommend this study, which is a guideline explaining ICC, the different types, what they do and how to use them and how to interpret them. Yeah, so this is very helpful. The SEM is something you find very frequently. One important thing for doing your own research is to not confuse it with the standard error of the mean. It's the standard error of measurement, which is the SEM, and it's calculated as the standard deviation multiplied by the square root of 1 minus any inferential expression of consistency or agreement. R can be Pearson correlation between the two. It can be ICC. It can be the Spearman if the data is not normal, and so on. So SEM, standard error of measurement, is an expression of error based on the deviation and your R value of any kind. So the difference is that ICC, because R can be the ICC, that the ICC is an expression of the agreement or consistency, and SEM is using potentially the same inferential expression, expressing the error that you expect. Also for this one, there is a good guideline that is helpful enough to understand it and to use it if you ever need it. The coefficient of variation is very, very common. And it's also very, very simple. It's only the standard deviation between two items divided by the mean of the two items. So this is an expression of the variation relative to the mean. And this is also a little bit problematic because it's only meaningful if the mean is relevant for the assessment of the variation. Usually, dividing by, for example, a mean or dividing by another variable is something we know from normalization. If you want to normalize sprint time, for example, by the length of your legs, because in your sample, all the people had different leg length, then you would divide, or one way is to divide the sprint speed or the sprint time, whatever you have, divided by the length of the leg. So whenever we do this, we do it because it's meaningful for the variable of our interest. So in this case, it's important to ask ourselves whether it's meaningful to divide by the mean or not. This is something I saw many times that was done where it was completely not meaningful. I want to give two examples. In the first one, it is meaningful to divide by the mean. In the second, it absolutely is not. I give this example to understand for you why it's so important to understand the test itself or to understand the variable itself. The first example is two systems measure the running time and they measure a 1 second difference. And the question is referring to the mean of the measured time relevant or not? Well, if you have two different types of running and they are very different in the total time required, for example, a marathon compared with a 100-meter sprint, then yes, it does matter, right? If you have this a difference of 1 second in the system by two different systems, then this 1 second difference is maybe very important for a 100-meter sprint because it matters if someone sprints 10 seconds or 9 seconds, but it's completely unimportant in a marathon run if someone, except for world record, maybe. But I hope you get the point. So when the measurement difference between two systems is only 1 second, and you have two different total durations, then yes, you should divide by the mean of them to have a relative value of this deviation. But in the second example, when you have two raters and they rate the performance of a dancer, for example, and the one judge gives 10 points and the other judge gives 9 points as a score, then you have a difference of 1 point. If for another athlete, the one judge gives 1 point and the other judge gives 2 points, you have again a difference of 1 point. So in this example, it doesn't matter what is the mean between the 2 points, because the difference between the two systems, in this case raters, of 1 point is independent of the mean of the outcome. Let's say if you apply a coefficient of variation in this example, then you would have a mean of 1.5 for the score of 1 and 2, and a mean of 9.5 for the scores of 9 and 10. In both cases, you have a difference of 1 point, but the CV for 1 point difference divided by 1.5 would be some 66%, right? And for 1 point difference divided by 9.5, it would be something below or something about 10% or something like this. So much smaller. But in the end, it doesn't matter. Both raters have a difference of 1 rating point. So it's very important to understand whether it's meaningful to divide by the mean or not. If it is, you can use the CV. If it is not, just use for example, the standard deviation or just the difference. So that's very, very important. The next one is also very typical. It's the root mean square error. And basically, it looks a little bit complicated, but in fact, it's quite intuitive and easy. It is the difference between each single collected data point that was measured and the true value. And sometimes the true value is lower, sometimes the true value is higher. So to avoid losing the error by averaging, because the average of error of -1 and +1 would be 0, but obviously you don't have 0 error if you have once a -1 error and once a +1 error. So to avoid this, you take you multiply by itself, and then you take the square root. So for a -1 error, you will end up with an error of 1, as well as for the +1 error. And then you divide it by the number of observations you did. So divided by n. It is in some way an average error that you will receive. And a specific type of root mean square error will be the standard error of estimate, which you may find when you dig into the literature, but it's only a specific type of root mean square error. Root mean square error is very popular, and I think also very helpful because it's very easy to understand. It's just you get, for example, an outcome value of 2 centimeters, and you know, okay, most of the error you have when measuring the position will be about 2 centimeters. Very easy to understand. And also for root mean square error, there is this reference I would recommend to understand it a little bit better. Another very, very popular one is the Blunt-Altman plot, or the limits of agreement that are used in the Blunt-Altman plot. There are also some critics about Blunt-Altman you can find by Hopkins on this link. But I think it's very helpful for visualizing and to identify where most of the errors are. The Blunt-Altman plot works in a way that you display the error of each single data point on the y-axis, and on the x-axis you have the outcome value of the mean between the two systems. So you can see the further the data point is away from the axis in the center, the larger the error, and whether it's left or right defines you how large the mean was. And this is helpful because maybe systems have a large error when they measure high speeds, but they have only very small error as long as the speeds are very low. And this you could find out very well in the Blunt-Altman plot. This would mean if you have low speed on the left side and high speed on the right side, you would have a small range of error on the one side with the low speed. And then the more the speed increases, the larger the error increases. This would be very, very clear to see on a Blunt-Altman plot. So I think it has a good purpose and reason to be used. And all of these have different abilities to express different types of error, or to be identified differently. So they have different purposes. I wouldn't say that one is better than another one, but it depends on your type of data and the reason why you do the study and what you want to express. About all of them, you can easily find very accessible information, and on Google, of course, in literature, so studies that present guidelines how to apply them, and also on YouTube. You can find so much information how to run these tests. The one thing we were missing so far in this topic is Pearson correlation and difference testing. And in fact, Pearson correlation and differences are something that are among the most common tests when assessing validity or reliability in systems, but they are very problematic. They are definitely not enough and not very helpful. And when a study confirming validity refers mainly or maybe only exclusively on correlation and difference testing, that's not very helpful for you. The reason is that a correlation analysis like the Pearson or the Spearman is only able to investigate the consistency and the linearity between two items. It's the linear correlation, as you know, that is investigated by, for example, Pearson. And this does not mean that things are the same. It only tells you that things behave in a linear manner. Two examples for when the Pearson correlation can be 1, so a perfect score, but the data is not the same at all, very clearly. On the left side, there is consistency. So both these data, sets of data, are consistent with each other, but they are clearly not the same. This is always one higher than the other one. And the other one has a perfect linearity. It's perfectly linear. If you enter these data points in your Excel by yourself and run a Pearson, you will get a correlation coefficient of 1, but obviously they are not the same. They absolutely do not agree with each other, but they are perfectly linear to each other. So these two examples are important to understand the difference between what a Pearson or Spearman correlation is able to do compared with true agreement between the data. And the second part is the difference testing. And the problem about it is, if you have a non-significant result in the difference testing, this does not mean that there is no difference. It just means that you were not able to show that there is a difference. So this is a difference. And if you have a significant difference, you also don't really know what is the level of disagreement. How much are they different? So both of them, correlation and difference testing, by itself and also in combination, are not good indicators of two systems being similar. To understand this difference a little bit more, the study by Berthold is very much recommended. As I was talking about correlation analysis now, and correlation analyses are something that maybe many of you will use at some point, I want to talk about another major problem that is often overlooked. It's not only in correlation analysis, but there it's very simple to understand the impact of this error if you do it. And the problem I want to talk about here is if you have hierarchical structure in your data. This means if your data is clustered, if in your whole data you have clusters, so single groups, and they belong to each other. So this group has similarities and this group have different similarities. The problem is if you ignore these groups, the fact that there are groups within your sample. And what you basically do when ignoring is that you treat data as unrelated, although in fact it is related. You know, usually you use a long format if you enter the data in your Excel. And in any column, you have a variable, and in some way it's related to the data in the other column. So columns are dependent to each other, they relate to each other, and rows are independent. In the rows you have your participants, for example, subject 1, 2, 3, 4, and so on. The important thing is that the subjects are independent to each other. If I make the run, I get my data in the columns. If my brother makes the run, he gets new data in the columns and so on. But my data is independent of the data of my brother and so on. But if you have dependencies between the subjects, then you have these clusters. This figure should explain how these clusters work. At the lowest level, you have level 1, the individuals. These can be subjects. And you treat them all as unrelated. They are all independent. But if in fact there is a level 2 above, and this level 2 can, for example, be a treating doctor. So one doctor has 2 subjects, and the doctor treats 2 subjects, and there is another doctor at level 2 that also treats 2 subjects, then both of these 2 subjects are not unrelated anymore because they had the same doctor. Maybe the doctor had a certain type of preferred treatment or something. There can be many levels. So maybe above the level 2, the doctors, there are clinics, institutions. Maybe 2 doctors are from the one hospital and another 2 doctors are from another hospital. And maybe within one hospital, they have certain regulations, how to treat subjects or certain best practices all the doctors have to do and so on. So this is hierarchical structure in your data. And you have clusters because more than one subject is within a cluster that is defined on the next level in this hierarchical structure. So again, the problem, the main point to understand is that the subjects are not unrelated and independent of each other anymore, but they belong to subgroups. This is very, very problematic for the statistical outcome. And the next slide will show why and how this can affect the outcome. So this figure shows you on the x-axis the number of bedrooms in the house, and on the y-axis the price for the house. And usually you would expect the more bedrooms a house has, the more larger the house, the more expensive it is. But this figure shows you the more bedrooms, the larger the house, the cheaper the price goes down. And if you run a correlation study, a Pearson correlation test on this data, you would confirm this observation and you would conclude, yes, the more bedrooms my house has, the cheaper it will be. It doesn't make any sense, right? The problem is that you ignored clusters. You ignored a hierarchical structure in your data because these data were collected from different areas. And the many houses you collected are from different parts of the city and region. The black dots are all from downtown, from the center, where houses are much more expensive. The red ones from the edge of the town are a little bit cheaper. Even more cheap are the suburbs, and the cheapest are the houses in the countryside. This makes sense in many countries. So now when you take a closer look, the trend within each of these clusters is a completely different one than the overall trend. In each of these clusters, you have a positive correlation. Now you see within countryside, you can say the more bedrooms, the higher the price. Within the suburbs, you can say the more bedrooms, the higher the price, and so on. But if you ignore these clusters, and you just run a Pearson correlation, you will think, oh, the higher the number of bedrooms, the cheaper my house. That's completely wrong, completely wrong. So this is why understanding your data, realizing if there are clusters and hierarchical structure is so important. And if you have this hierarchical structure, then the easiest way is to make the analysis only within each cluster. So run your Pearson within the downtown, within the edge of the town, within the suburbs, within the countryside. The problem is you can do this only if your sample size is so huge that the sample size within each cluster is big enough for the statistical test. And even then you have the problem that you run, basically in this example, 4 times the number of statistical tests. And as you know, in each statistical test, you have error likelihood of, we usually use 5%. So the more statistical tests you use, the more likely it is you find a significant result, and it's an error. The other solution, the better but advanced and more difficult solution, is to use tests for the whole sample of all clusters, but considering the clusters within the test. There are different ways how to do it. There are mixed models. There are multi-level regression models. I think the multi-level regression models are somewhat, I mean, not super simple, but maybe the easiest step to face these problems. And the reference I provided there can be helpful. Basically, how this works is that in the regression model, you add the different levels as an additional factor. And it's not too complicated, but very powerful. The important thing for you for now is to be aware of hierarchical structures in data and to check in your data if you have such clusters. You can also account for some clusters in ANCOVAs, for example. So you use an ANOVA and you add a covariant, which can be the area where the house is, could be a covariant in your ANOVA. These are relatively simple solutions for these problems. But be aware of clusters in your data. And another problem of correlation and regression analysis is that correlation analyses check a linear relationship between 2 items. And we often observe or collect data. We have 2 sets of data, and we want to know what is the relationship between them. And then we just blindly apply, for example, a Pearson correlation. And depending on the outcome, we say, oh, it has a strong relationship or it doesn't. But we often forget that the Pearson is only assessing the linear relationship. Things can have non-linear relationships, and the Pearson is simply not able to detect these. So we should first make a scatter plot of the data and see visually if there is any other than a linear relationship between the two data sets. In these examples, in the two above, we see there is clearly a relationship between the two data, but it's not linear. So if we run a linear correlation analysis, it will give us a bad outcome. This just tells you that the linear correlation is poor. It doesn't mean there is no relationship. What you can do is instead transform the data into something nonlinear. And then you can run a linear analysis on the transformed data. So nonlinear correlation analysis sounds a little bit complicated, but in fact it's not. And in fact, it's quite helpful because it's much more realistic in many cases. Whether you have nonlinearity in your data or not, you can check by doing residual plots. Basically, these work by calculating the residuals of between the data points and plotting them on an x-axis, which is dependent on the mean. And then if they are spread across the figure randomly, you have a linearity usually. If they show some clear patterns, then you have a different relationship between them. The way how to transform data into something nonlinear are endless, because basically you can use any sort of formula to transform them. But there are only a limited number of transformations that are meaningful. Because if you transform them too widely, you don't know how to interpret the data anymore. But some patterns are very typical in nature, and these can be represented by logarithmic transformation, here on the right side, and quadric transformations. Because very often in nature, you observe a slow incline, but then it's getting faster and faster and faster. Or the opposite, a fast incline in the beginning, and then slower and slower and slower. So when you see some relationships that look quadric in one way or the other, or logarithmic, you could transform your data. Just enter these formulas into your Excel and transform the data. And then you can run the standard correlation analysis, whichever you want to use, on the transformed data. That's still easy to understand and interpret and easy to do, but much stronger, obviously, than you just run a Pearson on the raw data and say, oh, there is no correlation. So it's important to understand what a test does and what it doesn't. And as I said, for the example of the Pearson correlation coefficient, it does not reflect agreement. So be very careful if people say, because a correlation based on Pearson was not significant or the coefficient was not high enough, the data seem to be unagreeable. Or moreover, it's the other way around, that a Pearson correlation is very strong and people conclude agreement between two things, but in fact, that's no guarantee at all. And it's also important to understand what a statistical outcome itself tells you. For example, the coefficient of variation, as I told you. Is the relationship with the mean meaningful for your data or not? You must understand what this outcome does, what it tells you, and apply it correctly. And the so I was talking about the coefficient of variation already. A second very, very simple example are the most fundamental outcomes every one of us knows: the arithmetic mean, like the average, the median, and the mode. And I think maybe not all people are super aware of what these things really tell you and how to use them. So because we all know them, I want to use them as a second example of understanding the statistical outcome. We all know that the mean is the average. So you have a set of data with different data points, like in this example, 2, 2, 3, 5, 5, 7, 8. And the average is 4.57. The mean is, as we all know, the value in the middle. So you display your data point as a sequence, and the one in the middle is the median. The mode is the one that is used most frequently. So as you can see in this example, there are two modes, 2 and 5. And then you also have the range. It's simply the maximum minus the minimum. It can also be interesting to know what is the range of errors we're dealing with, for example. So usually what you say is that the mean is easily affected by outliers, which the median and the mode are not. So even if there was another value, the 150, the median would be 5. And the mean would be very much different. So if you struggle with dealing with outliers, then maybe the mean is not the right tool, but the median is. This is probably what everyone agrees on and what you all know. So the median you use when you have no normality. Normality is something that is required to display a meaningful mean, and if you have outliers. The mode is simply something completely different for a different purpose. It is used meaningfully if you are interested in the value that fulfills the need of most people or has the most appearances. So it's not about, sometimes people think about the median being worse than the mean, and you only use it if you cannot use the mean, and they think the same about the mode. But in fact, I think it's just something completely different. So for example, if you are a company and you want to sell something to the largest possible target group, you are not interested in the mean interest or desire of the people. You are interested in the mode, because you are interested in the interest or desire that appears the most frequently in all the people. So you can sell it to the largest group. So I want to reflect on these three parameters differently. So they are different, they have different purposes. It's not about worse or better. Yeah. One more word about the median and the mean. As you know, the median does not require normality, which the mean does. So this implies another thing that is sometimes forgotten. And this is when you run your statistical test and you make, for example, you want to assess the difference between two groups, and you check if the data is normal distributed. And then you find out the data is not normal distributed. So you don't run a t-test, but you run, what is it, u-test? And if you find out the data is not normal distributed, so you take a non-parametric test, but then you provide mean plus standard deviation, you now realize that's kind of conflictive. It doesn't make sense. So I have seen this many times in articles I needed to review, where people use a non-parametric test because of non-normal data, but then they provide the mean. So that doesn't make sense. Or the other way around. It's normal distributed, and they run a t-test, but then they provide a mean, and they don't really have a rationale for why they use the median, and they don't have a rationale for why they use the median. It doesn't make sense. So mean and median, it's at least I don't want to generalize it, saying always or ever, but check if it makes sense with the test you choose. Okay, so understanding the meaning and the application of all the outcomes of your tests and so on. There are so many different outcomes you can calculate. And if you have diverse outcomes, so different ones, not only one, but maybe an ICC and a coefficient of variation, or a standard error of measurement and an ICC, and so on. If you have different ones, you can make more comprehensive reflection of the data. You can understand the data and the outcome in a better, more sophisticated way. This provides you more detailed information. It simply tells you more about the data, and it allows you for more in-depth analysis for your discussion. So the better your analysis is, the more comprehensive you reflect the data, the easier it will be for you to make a discussion in your manuscript that is sophisticated, that represents reality more closer, and so on. And all these things basically lead to increased quality of your work in the end. There are just a few practical things in the end for when you present your outcomes, when you use figures. The most important things, I want to just go briefly through it and then we're done. Use big letters, so it's easy to read them. Don't use unnecessary decimals like 0.001257 and so on. Don't use any distractions, visual or in terms of numbers. Make them black and white so they can be copied easily and still understood. Add descriptives to your figure so people can see the actual values. And you can also add the statistical tests if they are not already in the text. And explain everything you use in figures. So if you follow these, you have an example on the right side, bottom of the slide. So the letters are big, you have statistical tests, you have the real values like mean and standard deviation. Everything is explained, hopefully in the notes below, and everything is clear to see and to read, and it's not overloaded yet. And the other example in the upper left, you have small letters. It's hard to read them, and colors are not very distinguishable. So if it is printed in black and white, it's questionable how clear it is to read and understand the figure. And also overloaded with 3 or up to 4 decimals, unnecessary. Okay, and submission and review stage I will skip because it's not relevant to everyone, maybe. Yeah. Okay, I added some links in the end, and I think it may be good I share slides and so it can be shared later on with anyone who's interested, because I added the references with some guidelines during the statistics and also the links, so everyone can have it if needed. Okay, that's it from my side.
Okay, thank you very much, Dr. Philip. It's very excellent presentation and also easy understand to us. And it is also new knowledge for us how to write statistic. Usually we just use mean and ST, and now we can use modus, right, and median to write in the results. And now if anyone one question, you can raise your hand. Okay, Professor Sugianto, welcome. Belum di-unmute, di-mute dulu. Di-mute dulu. Not yet, belum dengar, di-mute. Okay.
Okay, Mr. Philip. Your presentation very, very excellent. My question, how about the field research during pandemic in Taiwan? Okay.
So can you repeat the question, please?
Field research during pandemic in Taiwan. Field research during pandemic in Thailand.
During the pandemic,
Yes.
in Taiwan?
Yeah, Taiwan. Yes.
Yeah. What is your question about the pandemic in Taiwan? Sri, can you help out? I didn't understand what is the question about the pandemic in Taiwan.
Yeah.
The Professor Sugianto asking about the research during pandemic. So do you have experience during pandemic? What research you do and how to do it? Is it in the laboratory or you did in the people, even though they at home, and how you write the results?
Okay. Yeah, thank you for the question. During some periods of the pandemic, we had no measurements. It was not possible to invite participants and to work with other people on the campus. So a lot of the time I was not on the campus. I was working on data we collected already before, or we still had from previous studies, and just working at home on data and writing. But it was not always like this, and it was easier for staff to go back to the office, even if it was not possible to work with other participants. But for us, it was possible to go back to the office and work together.
Is it okay, Prof. Sugianto? So, what usually data you took when during the condition of pandemic?
Yeah, so data can be very, very different, and of course the statistics you need depends on your data. So that's why I decided for this session, it didn't make too much sense to go into too specific details for one statistical test, for example, because Maybe only one person will ever use this test and no one else. I use most of the time biomechanical data. So a lot of continuous data like joint angles, joint velocities, the path of the center of mass, ground reaction forces, and so on. And so, yeah, experimental data, quantitative testing.
So you usually use quantitative data. How about the qualitative data you ever used during pandemic?
I used qualitative data only when I was working some years ago in a project, in a research project, where it was about perception of student athletes. It was a very different topic. It was about their career of young people and how they combine sports with education. And there they struggle a lot with pressure, with organization tasks, financial problems, of course, also. And for these studies we did in this field, there we used qualitative data also to create a better understanding of the problems they face. And statistics can be very, very different then. But most of the data I use nowadays and most of the studies I did were biomechanical. And it's either related to sports technologies or movement analyses. In terms of sports technologies, much of the things is having a device or a system and checking how well it works. For example, I was working on the local position tracking, or also another big topic was when we cooperated with a company who developed sensing pressure in soles and to investigate how accurately they measure the center of pressure. So validation studies are also a possibility to make simple research, I would say, requiring not much money, not much technical equipment when you cooperate with companies. So you can do the research for a company to test their devices. They give you the devices for the testing, and you don't really need a lot of other technical equipment or expensive equipment. And then from then on, it's just a matter of using the best statistical solutions for testing the validity and precision.
Okay, thank you, Dr. Phillips. Any else question? Hello? So you can directly ask me and raise your hand. Dr. Firdaus Henry, you want to ask me something? Dr. Siti Baitul. In here also have from other university, Jakarta, University of Jakarta, Dr. Arya Timul. Still here?
Ya, Mbak Sri.
Oh, semonggo. Yeah.
Ya, terima kasih banyak ini unofficial invitation soalnya dapat dari Pak Dekan UNJ.
Yes.
Alamatnya. Terima kasih banyak ini webinarnya. Terima kasih untuk semua panitia ya.
Okay. Yeah, sama-sama.
Good afternoon, Mr. Phillips. How are you?
Hello, nice to see you.
Nice to meet you too. So actually, this is a very interesting webinar, and I'm very interested with your presentation. It's very enhancement So actually, there are a few questions I want to ask, but I want to maybe give some two questions first. The first one is how can we determine our research novelty to be published in a very in a recognizable journal, maybe some journals that indexed by Scopus or WOS? That's the first question. The second one is I still have a problem in determining my pattern in statistical steps. So if we meet some really abnormal data, so it is better for us to take non-parametric test right away, or we try to transform it until it's really normal, and then we took a parametric test. So there are two questions for me. Is it understandable?
Yeah. Okay.
Okay,
So
thank you very much.
Yeah, thank you for the question. So the second question, I would first try to, in terms of how the data is collected, how the participants are chosen, and so on, to get the normal data, normal distributed data, or the type of data that is suitable for your statistical test. If this is not possible, transformation is okay, I think. It's a good second step. And then the third step, yes, using non-parametric tests is the way to go then. But first, I would try to get the data for a parametric test, if it is possible. If not, then use the non-parametric test. The first question about novelty.
Yes, novelty.
Sometimes statistical tools can add to novelty, but my impression is that most of the times that's not enough. It's more about the topic itself. If something was investigated already or not, and how huge the potential impact of the study is for health of society or whatsoever. So I think the more important part is to ask the right questions that are not answered yet.
Okay,
so very much a matter of introduction.
Yes. One more thing. One more.
Yeah.
So.
Oh, I think he's gone. For me, at least, I cannot hear him.
Maybe the internet is not connected. Hello, Dr. Firdaus.
One.
Yeah. Okay.
Check.
Yes.
Putus ya. Okay, sorry. So actually, there is a. Is there any theoretical articles or maybe some theories that could be based for us to determine the minimum number in doing quantitative research?
Doing what?
Quantitative research.
Minimum. So how much
Number
participants?
Yeah.
Yeah, the participants on samples.
Oh,
So
yeah, yes.
Okay.
Okay.
So there's have a rule, less for maybe minimum is 10 or something.
Yeah. So the practical, I would say non-evidence based explanation or statement is that many people use like 10 or 12 as a minimum. This is also many times simply based on the size of teams. So especially when you do something with high-level athletes and so on, you have access to only one team. This seems to be a number that is often realistic and not much more than this. So people kind of accept a sample size of 10, 12. but below they tend to prefer then having non-parametric tests simply because of the sample size. If you can have access to a larger sample size, for example, you are investigating nothing really special in terms of sample characteristics, not elite athletes, but just let's say healthy people, nothing special. Then 10 or 12 would probably be too less. Then you should rather go for 20 or something like this, 20 and above. And more than this, I cannot really generalize, because then it depends strongly on how many characteristics you have in your analysis. For a simple one-way analysis between two groups, 20 or 25 would probably be good enough. But if you have a two-way analysis or different factors in a regression model and so on, then you need larger samples. So it depends very much on the specific data then, in fact. But as a general thumb of rule, when you have special characteristics in your sample, like elite athletes, people tend to accept 12. If not, rather go for 20 or more. And
Okay.
if you can, add the statistical power analysis. Reviewers are very quickly silent. If you say, oh, power analysis done and this is the result, then it's fine.
Okay, thank you, Mr. Philip.
You're welcome. Thank you.
Thank you, Dr. Firdaus Henry. Is it okay? So now the time is up, and thank you very much, Dr. Phillips, for excellent presentation and make us easy to understand about statistics. And maybe next time you're welcome to come to UNES, like Michel Starczewski. He planning for next year to come here. So maybe you can plan to hear also.
Yes, regulations get looser and looser. It's getting more simple to travel again.
Yeah, how about Germany? No,
Germany is relatively easy. Taiwan was the problem because they had quarantine for 14 days, but already now they have for only 7 days. So if they change it further and make it more simple, then yeah, looking good for the future.
Okay, before we are finished, this have a certificate from Professor Sugianto. Okay. I mean, may I share the screen? Wait a minute. I'm looking for here. Sure. Different with detail. Can you see something? No? Cannot see something?
Not yet, still process.
Maybe Miss Maria, would you help us to share the certificate?
Okay.
Thank you very much. And I hope everyone in here can understand Ms. Phillips' presentation And we hope this knowledge will help us not only to finish study, also in the research. Not yet? Why? What happened? Okay. Professor Sukianto, now is your time.
Okay, Mr. Philip, this certificate for you. Thank you very much.
Thank you. Thank you.
Okay.
Maybe this is a certificate, but we are, thank you very much for sharing knowledge to us. And hoping someday you can come here and to be one of lecture in here next time.
Yeah, would be very nice.
Thank you very much.
Thank you very much for the invitation. Thank you.
In here also have Dr. Stella Hayu. Maybe you want to say something to Dr. Phillips.
Okay, thank you, Dr. Philip. Yeah, see you next time in Indonesia.
Yes, see you again.
Okay, see you.
Thank you, Dr. Phillips.
Masih di mute, Mbak.
Okay, thank you. Before we have finished this presentation, this guest webinar, we would like to take a picture together. Please open your camera and give sweet smile. Miss Maria, would you please to take down the certificate and we take picture together. Thank you. Okay. Oh, here also have Professor Sugiharto from Sport Science. So, welcome, Professor Sugiharto. Okay, please open your camera and give me your smile, big smile. Okay. Cheese. Hey, one more. Okay, one more. Nali. Oh, where is this? One more. Cheese. So this the people who still enjoy the webinar from 90 to 42, just 0.5%. And here also have a Dr. Arya Timur from Jakarta University. Welcome. So, and thank you for our participant. Also have a from Kediri at UNP Kediri. I saw. Thank you very much for your participant in here. See you in the next webinar. And we will have webinar on 8 June about exercise physiology with Professor Jia Hua Kuo from University of Taipei. So please note the date and the time.
Thank you very much, Ms. Sri Sumartini.
Thank you.
Bye-bye. Have a good evening.
Good morning for Phillips.
Thank you.
Thank you.
Good evening soon.
Good
Bye-bye.
evening and have a nice day. Barakallah.
Tin. Thank you.
Matur suwun.
Ya, thank you, thank you.
Ya,
Bu
thank
Titi,
you.
Bu Setio, Prof.
Ya.
Ki.
Ya, terima
Oke,
kasih Bu
Ya,
Paito.
makasih.
Thanks also Maria for help us.
Yes.
Makasih Bu Titin, Bu Setia.
Ya, sama-sama. So,
Okay, Jen, left to you.
The webinar in June is held by Professor Kur.
yes, welcome to
Ah.
join.
What time is it?
I think it's about at 10 usually, or maybe after at 1.
Okay.
Yeah, about exercise physiology. So welcome.
Maybe I can join.
You still in German or will be back to Taiwan?
Which date?
8 June.